Okay, section 7.3. We're going to learn some new identities. There are three categories, double angles, squares, and half angles. We'll go through them one at a time, but if you want to print them out and have them as a reference, here's a page where you can print them all out. So here are the double angle formulas. It's a formula for sine of twice an angle. So if you know the sine and cosine of an angle, this formula will allow you to find the sine of twice an angle. Just to try to show you where the formula comes from, we're just using the formula for sine of s plus t. So sine of 2x, that's the same as the sine of x plus x. And so we apply the formula for sine of s plus t, where both s and t are x. And that gives us sine times cosine and two of them. Okay, so you don't need to know that derivation. You just have it on your note card, this formula. Okay, so here's the example. We're going to compute sine of 2 theta given some information about sine of theta. We're told that sine of theta is 3/8, curious number, and that theta is in quadrant 2. The angle is in quadrant 2. Okay, so this is what we're trying to compute, sine of 2 theta. So we use the identity. Sine of 2 theta is twice sine of theta times cosine of theta. Well, sine of theta, that's given in the problem statement. It's 3/8, no question. Cosine of 3/8 is something that we need to take a time out and find. Right? How do we find cosine of 3/8? Well, one way to do it is to solve for cosine, solve this Pythagorean identity. So we get cosine is plus or minus, we've done this many times, plus or minus the square root of 1 minus sine squared. And then because of the quadrant location, quadrant 2, we know that the cosines are negative in quadrant 2, so we pick a minus sign. So finally that allows us to compute the cosine for theta. The cosine for theta will be minus 1 minus the sine for theta. And again, that's part of the problem statement. The sine for theta was 3/8. Okay, so the answer to this problem is going to be 2 times 3/8 times what turned out to be the cosine of theta. Right, so we weren't really asked to simplify, so we could probably just leave it like that. I will simplify it just a little bit. The 2 and the 8 cancel down to 4. And I'll put the minus sign, the minus sign out in front. I think that'll look a little bit better. And then I won't bother trying to simplify down the radical at all. I'll just leave it like that. Okay, so that's the formula for sine of 2x. Here's in fact, 3 formulas for the cosine of 2x. Like, oh, what a nuisance, I have 3. Well, they're going to be on your note card, and it's actually nice to have all 3. You'll see that sometimes one is much easier to use than the other. Just a quick look on where they come from, these formulas. Again, the idea is to take cosine 2x and write it as cosine x plus x, and then use the formula for cosine of s plus t. Okay, so both s and t they're both x's. So we just fill in the x's, and sure enough, we get cosine squared minus sine squared. And then for the other 2 formulas, it's simply taking this first identity, and in one case, replacing the cosine squared with 1 minus sine squared. That's what leads to this second identity. And alternatively, if we replace the sine squared with 1 minus cosine squared, that's what's giving us this other identity. This parentheses there. Okay. All right, so let's look at an example of using this. If sine of, I don't know. Why? I could leave it as x, but I don't, for whatever reason, I don't like to have thetas in here. I like x for kind of the generic formula, but for a specific one, I want Greek letter theta. So we're asked to find cosine 2 theta. Okay, so again, remember we have all 3 identities at our disposal. Right? Which would be the best to use here? Well, the best one to be using here would be to use the one that only involves sine, because that's the information we were given. If we tried to use either the first or the third identity, we would have to take a time out and try to figure out what cosine of theta was. So pick the one that only requires sine, namely this one. And then I'll just replace the x with the theta. Don't know if we really need to do that. All right, so again, it's given in the problem statement that the sine of theta is 1/2. And that's what needs to be squared here. And I guess we weren't asked to simplify, but this is going to simplify so nicely, I feel compelled to do it. This winds up being 1/2. Okay, so do keep in mind always that you've got these 3 different possibilities for cosine 2x identities, and pick the one that works best. So the text also gives formulas for tangent of twice an angle, and I think maybe secant of twice an angle. On the exam and quizzes, I'm going to focus on sine and cosine. If it comes up in a web work that you need a formula for tan of 2x or secant 2x, simply look them up. They won't be on the exam. Okay, so that's one of the categories, double angle formulas. Another category here is formulas for sine squared and cosine squared. Now, of course, we already have a formula for sine squared. We can write it as 1 minus cosine squared. But this formula is trying to tell us what the sine squared is going to be, the second power of sine, based on just the first power of cosine. And cosine squared is also expressed in terms of just the first power of cosine. These are called power reducing formulas. And they're useful for your calculus class, and you'll need to try to remember these formulas for that class. All this is doing is simply taking the identities for cosine 2x and solving for the squared parts. I don't know if it's worth even watching. I guess we can leave it in the PDFs. Right, we simply solve these identities for the squares. This is if you've heard me talk about cosine as being contrary and oftentimes having negatives in its formulas, this is a rare instance where the cosine squared has the plus sign, and it's the sine squared that winds up with a minus. Who knew? Okay, so a couple applications. Find sine squared pi over 8. Well, first, let me say, find exact value for sine of pi over, this means, you're supposed to, excuse me, you're supposed to compute sine of pi over 8 and then square it, but can't find exact value since we don't know sine pi over 8. So that's why we're going to use this identity, right? So we use the identity. So sine squared is 1/2 1 minus cosine of twice the angle. Our angle is pi over 8. And of course this has been set up to work out such that twice pi over 8 is an angle that we're familiar with. Okay, so this is 1/2 1 minus, what is this, root 2 over 2. And we won't bother trying to simplify that either, just leave that as it is. It is an exact value. Okay, so here's another application of this power reduction. If we're asked to graph cosine squared, we're sort of sunk, because all we've been trained to do is to graph transformations of cosines and sines and tangents. And this isn't a simple transformation. Okay, so what we're going to do instead is rewrite this using the trig identity. Right, so the trig identity says, well, y equal cosine squared x. You can rewrite that as 1/2 1, let's see, yeah, plus cosine 2x. And then I'll expand that out, just multiply out the 1/2. Okay, so this function has now been rewritten as a translated or transformed cosine function. What's the period? Well, the k number here is 2, so the period is 2 pi over 2 equals pi. What's the amplitude? Well, that's the 1/2 in front of the cosine. What's the horizontal shift? There's none. And what's the vertical shift? There's a 1/2. Right? And that's all the information that we would need to get a fairly decent hand sketch of this function. And this is what it would look like. You see that the center line is at a 1/2. That's the vertical shift. The amplitude, we go from a 1/2 up to 1 and down to 0. The amplitude was a 1/2. No vertical or no horizontal shifting. Right? And the period from peak to peak, that's from 0 to pi, is pi units. Okay. One more application here. So this is where they get their name sometimes. We're going to reduce the powers in this expression. And we're going to do that by replacing each of the squared trig functions with the trig function only to the first power. I missed that. So but it's not going to matter in the end, but I should try to get it right. So that's applying the two identities, one for sine squared, the other for cosine squared. And now I'm going to try to simplify. The 1/4 comes out in front. That's a 1/2 times a 1/2. And this is 1 minus cosine 2x, and then 1 plus cosine 2x. And on the next step, what I'm going to do is use the formula this algebra formula. This is not a trig identity. This is the a minus b times a plus b equals a squared minus b squared. So maybe this goes up on the previous line. I don't know where to put it. But this is a minus the b, and here's a plus the b, a squared, namely 1 squared is just 1. Okay, so the instructions here are to rewrite this in terms of a single cosine to the first power. So we've still got cosine squared. Here we had 2 cosines, so that didn't work. We need a single cosine. Okay, so it turns out all we need to do is bravely replace one more time. What we're going to do is replace this cosine squared, again using the identity for cosine squared. So cosine squared is 1/2, excuse me, 1 plus cosine, beg your pardon, of twice the angle. Now our angle is 2x, so when we double that, we are going to get 4x. I think I have the correct number of parentheses there. Right. We could definitely try to simplify that a little bit, but we've met the letter of the law. There's a single cosine in here, and it's to the first power. All right. Half angle formulas. So this allows us to compute the sine and cosine of half x when we know the cosine of x itself. Okay, so just to show you where the identities come from, what we do is we take the identities for the squares, replace the x in those identities with, say, u over 2. Okay, so when I replace the x with u over 2, this becomes just u. And then I'm going to take the square roots of both sides. And when I do that, I have to use plus and minus. And I think this is the way the book actually lists this identity with a u here. But after doing the derivation, I prefer to go back to the letter x and have all the identities written with x's. Okay, so we'll do an application here, try to compute sine pi over 8. Again, we want the exact value. And we don't know it. We don't know our pi over 8s. We do, however, know our pi's over 4, and so that's the key observation here. And so we can use the half angle formula for sine. I don't know, maybe it would be more helpful to write it this way. So we're using the formula for sine x over 2. So that is going to equal plus minus the square root of 1 minus the cosine of pi over 4, aha, an angle we do know, divided by 2. And it is up to us to choose the correct angle, I mean, beg your pardon, the correct sign. And the correct sign here is positive, and this is plus, since pi over 8 is in Q1. Okay, so we're not done here. I think in order to exit this problem, we need to evaluate that cosine. So that cosine of pi over 4 is root 2 over 2. And that's a nasty looking expression, but it is an exact value, and we've evaluated the cosine, so I think we can quit there. I'm going to do 3 homework problems. I think I might have assigned these problems. I'm not entirely sure. They were a little bit difficult, I thought, so I'll do them for you here. So problem 29 asks you to simplify this expression, and it looks a little daunting at first, and it might be hard to be inspired on this. So what we're going to do is use this identity for sine squared x. I mean, why? This doesn't seem to have anything to do with sine squared x. Well, remember what this identity is. This is twice sine x cosine x. And we just have to be slightly inspired here to say, oh, we can take this identity and solve it for sine x cosine x. All right, so we're just dividing both sides by 2. And now we're going to apply this new identity, replacing x with 3x. Okay, so when we do that, we get sine of 3x times cosine of 3x equals 1/2 sine squared of 3x. And I think that that's what's considered to be the simplification here. Okay. Eliminating the trig functions in this expression. This is the type of thing that we've seen before. What we're going to do is, it's a trig of an inverse trig. So we're going to get a triangle whose an angle of which is has tangent x. Well, I didn't say that very well. Right, so we want this to be the inverse tangent of x down here. Okay, so that says that the opposite should be x, the adjacent should be 1, and we can get the hypotenuse then. Square root of 1 plus x squared. Okay, so now we can use the formula for sine of 2x. Ooh, this is going to be unfortunate. I should have given that a name, that angle. I'm just going to refer to it as t, I guess. So this is twice sine of t times cosine of t. And then from the triangle, we read off those two values. So the sine of t is opposite over hypotenuse. And the cosine of t is adjacent over hypotenuse. I guess it's kind of compelling to simplify that. We have 2x upstairs, and because we had the 2 square roots downstairs, that's why I felt compelled to simplify that. Sorry, I should have called this this angle down here t. Okay. evaluate this. So this is an evaluation problem. So we want a numerical value in the end. Okay, so let's see. I told you I wasn't going to ask for secants, so we're going to re-express secant in terms of cosine. So this is 1 over twice cosine, 1 over cosine twice sine minus 1/4. Oops, okay. So what's important to remember is that this inverse sine here, that's an angle, right? So this is cosine of twice an angle. We want a formula for cosine of twice an angle, right? We've got 3 different formulas that we could choose from for cosine of twice an angle. Oh shoot, I'm scrolling back to them again. Forgive me for my scrolling. Be right back. So we can use any one of these 3, and I think the best one to use, again, is going to be the one that has just the sine involved. Okay, so cosine of twice the angle, that's going to be 1 minus sine squared of the angle, and our angle is this weird thing, squared. All right, this is a complicated looking algebraic expression, and part of what's confusing here is this weird notation on the squaring. Remember what that is, though, is we're supposed to take the sine of the angle and then square it. And now, yeah, the number of parentheses here has just gone crazy, hasn't it? Right. But the nice bit now is that we're taking the sine of the inverse sine of 1/4, and because 1/4 is in the domain for this function, this inside thing simplifies down to just 1/4. Right. Lastly, this is simplifies down to 1/16. I think this would be 1/8. I said lastly, and then I didn't leave it alone. So I think this is going to be 8/7 in the end. My arithmetic might be off on that just a little bit. All right, we're at 22 minutes. Good news here. I'm going to skip this section, product to sum identities. I cover it sometimes, but it doesn't come up in a calculus class that I can recall, so you'll be okay not to look at those, I think. And then these other identities, sum to product, I'm skipping those entirely, as I always do. So we're not covering everything in this section, but 3 big categories. Okay, that's it for 7.2. That is to say 7.3.